Wonderful. All right. Good afternoon, everyone. It's so great to see you all. And as the quarter ends, the academic year will continue in January, but I hope that you're finishing up the quarter well. And I'm very pleased to introduce our visitor here. This is going to be a great talk. My colleague, Professor Hyungbo Shim, coming from Seoul National University. And let me say a few things about him. He received a Ph.D., a master and a Ph.D. from Seoul National University. He was a postdoc at Santa Barbara, University of California, Santa Barbara. We didn't overlap, right?
We didn't overlap. My stay is 2000.
2000, so it was a year late. And since then, he's been also a professor at the university, Seoul National University. He's been associate editor for the top journals that we publish: Automatica, IEEE Transactions, Automatic Control, International Journal on Robustness, Nonlinear Control. He's also a senior member of IEEE. He's also a distinguished lecturer of the International Federation of Automatic Control. And also he's the general chair for the upcoming IFAC World Congress in Seoul.
Yeah, it's Busan.
Korea. I don't know where?
Busan is another city.
Busan. Okay, sorry. And another thing that is very important is that he's also a member of the Academy of Sciences and Technology in Korea. So with that distinguished record, I would like to also say that he has very interesting research flavor and love for things that we also love. He's going to be talking about multi-agent systems. He is very interested in synchronization, observer designs, secure control system, nonlinear control, and many other things that we're going to learn today. And very excited to have you here. So welcome.
Yeah, thank you very much, Ricardo. Thank you. Yeah, good afternoon, everyone. I'm really excited to see this campus and see all of you and have a chance to share what we have found regarding the multi-agent system for the last 10 years. So thank you very much for coming. Maybe 15 minutes is the okay, yes. Okay, so let me start. So today what I'm going to do is I'm going to talk about some emergent behavior, robustness, adaptation. I think those keywords are quite common in multi-agent systems. So people are studying these phenomena. And also, it's not from the control community. I guess physics, biology, social science, most of them are interested in this keyword. But their approach and control theorist approach is slightly different. That's what I feel. What they do is they have some insight, some principle, and then they verify their principle by some simulation or observation or experiments. Control theorists, I think, we prefer some mathematical model, and we do the mathematical proof, and we want to have a rigorous and complete argument, even if it is simple. So today, what I'm going to do is we just follow the control theorist viewpoint regarding these three keywords. So in order to do that, let me begin with the very well-known so-called average consensus, which is quite became common in early 2000 in the control community. So what I'm saying is here, we think about capital N agents are connected using some communication. So for simplicity, we just think about integrator here. So xi dot is integrating this right-hand side. The right-hand side is a so-called coupling term. I think most of you already know this kind of multi-agent system, right? Otherwise, I can just go a little deeper in here. So, yes. So,
usually there's a weighting coefficient on that.
Right. So that's a good point. Thank you. So we are going to make use of the weighting later. So this is just a simplest form. So xj is received information from the neighborhood of agent I. And then what happens is that, so this is just a basic idea. So if you have a communication graph, and people can describe this communication graph by so-called graph Laplacian matrix, which is denoted by L. And then if this graph is connected, then always there exists a single eigenvalue at 0, and all the other eigenvalues are positive numbers, so that the kernel of this matrix L contains the all one vector, meaning that all elements are 1. And then using this information, we can develop another orthogonal matrix R, which acts like a similarity transformation of this Laplacian into 1, 0, and all other positive definite matrix lambda. Okay, so that's, I think this is well known. So if we write down everything in a single equation, we have this equation. Okay. And then now we apply the coordinate change from this overall system into some special coordinates, so-called Z, O, and ZX. And ZO is nothing but the average of individual states. And one good thing of this state transformation is that actually X consists of these two terms. And then ZO is actually describing the behavior of the collective one. And ZX is the measure of consensus. So if you achieve consensus, meaning that all the states converge to each other, then the value of Zx becomes 0. So the ZO is actually governing the overall behavior. So if we apply this coordinate change, we end up with this simple equation, and we immediately get to know that Zx will go to 0, and ZO is just to remain constant. And its initial condition is nothing but the average of the initial condition. So what we can conclude is that as time goes on, all the agent goes to the average of initial condition over everyone. So that's the average consensus, which is already...
Is lambda in that equation, is that positive, definite, or...
diagonal.
What?
Even
diagonal.
Yes.
Okay.
Yeah.
Okay.
Right. I just said positive, definite. Yes.
Thank you.
Yes. Okay, so in the past, people say this phenomenon is the emergent one because no one is adding up all the initial conditions, no one is dividing by n, but just computing the average of initial condition like this is an emergent behavior. Okay, but what about if we add more dynamics here in front of this coupling term? And here Fi means they are all heterogeneous. Depending on individual agent, they may have a different vector field. So what happens? Well, we can immediately see that consensus is hopeless. Because even if you start with the same initial condition for everyone, the Fi are all different. They are pointing out different directions. So as time goes on, you don't maintain the consensus. Okay? So in that case, we have a tool which is pressing or enforcing the consensus by introducing the weight k here. So as you mentioned, we multiply the positive number k in front of this coupling term. And if you increase the k, then it's actually pressing or enforcing the consensus somehow. So we can expect that approximate consensus can be achieved as time goes on. So that's somehow expected, that's somehow well known. But our interest is not just the consensus. Our interest is for what? Why we need a consensus? After achieving this approximate consensus, what happens? That's our interest. So the next question should be, what does the state xi do after they achieve the approximate consensus? That's the question. And then regarding that one, I want to introduce so-called blended dynamic theorem, which is summarized in this single page. I think the Mohammed visited your lab before, right? There was a postdoc here. Yeah. So he has a similar result, like this kind of thing. So what we can expect is that we have a heterogeneous multi-agent system, okay? And then the graph is connected and strongly connected and balanced. And then here we define so-called blended dynamics, which is simply the average of this heterogeneous vector field. So this is a virtual one, right? And then once we assume this pink blended dynamics is contractive or stable, in other words, then we can conclude that there exists a threshold K star such that if your coupling gain K is greater than this threshold, then all the agent Xi will converge the behavior of S of T with the error size of big O of 1 over K. So it's proportional to 1 over K. So if you increase K, you get smaller and smaller residual error in the end. So the meaning is that all the agents will behave following this dynamics, so-called blended dynamics. So here, blended dynamics is a new one because none of the agent has this vector field. It's a somehow combined one. So if you imagine them Lego blocks, so you have many different blocks of Fi, and then you can just add all of them, and you make a new behavior of the dynamics. And another one that I want to note is that I assume the stability or contractility of this blended dynamics, but I don't assume stability of individual agents. Okay, so keeping that in mind, well, this is the brief one-page proof of the blended dynamic theory, which is the following. As we did before, just apply the linear coordinate change so that you get ZO and ZX. But this time, ZO dynamics looks like this one. The ZX dynamics looks like this one. So if you increase the coupling gain K, this system becomes a singularly perturbable system, or this negative term will dominate the residual term. And the meaning of this residual term is a measure of heterogeneity. If you have an identical agent, this term disappears. So somehow large K is pressing this difference. And then finally, Zx will converge to the small value. And when Zx becomes a small value, then what is remaining is the same as blended dynamics. So we can say that the blended dynamics is nothing but the quasi-steady state subsystem when you increase the gain K sufficiently large. So this is one interpretation in terms of singular perturbation theory. Another interpretation is blended dynamics is a zero dynamics. What I mean is the following. You have a multi-agent system. You treat the individual coupling term as the input to individual node dynamics, and you think the output is the graph Laplacian times the stage. Then, if you compute the zero dynamics of this multi-agent system, you end up with the blended dynamics. So meaning that if you use the high gain of static output feedback, then what is the remaining dynamics is the zero dynamics, which is again blended dynamics. So that's the interpretation of the blended dynamic theorem. So I can skip the proof, but now let's go back to the original question, which is this blended dynamics can explain this behavior or not. That's the question that I want to explore in this talk. So first example is this. Let's think about this dynamics. Here you have a multi-agent system. And agent number one is integrating 1 minus x1 and communicate. And all other agents is just simply integrating number one. So what are they do? What they are doing now? Well, it's not very visible. So let's compute its blended dynamic, which end up with this one. Why? Because the average of 1 is 1. Average of minus x is now is S over n. And this pink blended dynamics is stable one, so S will converge to number n, right? So all the other agents will converge to this number n with the error proportional to 1 over k. So we can say that this is a network size estimator. So no one is counting how many members are in this group, but each member just integrating number one and communicate except agent number one, and then everybody converge to how many agents are in this group. So this kind of behavior is an emergent one, right? Only there are no centralized unit. They just distributedly communicate with each other, but they figure out the number of agents. So in that sense, we can say the stability is emerged because number one is not stable vector field, but stability emerges or traded with agent number one. That's another emergence behavior of multi-agent system. So this is one example of emergent behavior. But if we think about the nature, robustness is also very important one, right? So let's look at this simple example is still robust with a small perturbation one. So in this case, I'm talking about many agents is running this algorithm, but sometimes one agent is leaving the network, or sometimes a new agent is joining the network. So let's think about that kind of situation. So in the left-hand side, this is well-known average consensus. And this algorithm also gives you the number of agents in this way. you set its initial condition 1, you set all the other agents 0, then they converge it to 1 over n because they converge it to the average of the initial condition. Okay? Now, on the right-hand side, you see the algorithm based on the blended dynamics. As I said, this goes to n. So which one is robust with respect to the joining or leaving agent? On the left-hand side, once they achieve this consensus and one agent leave the network, then the number n is now changed, but nothing happens. They just remain 1 over n, right? But here, if one agent leave or added, then this blended dynamics is changing because the average is changing the average of the vector field is changing, so that you convert it to a new value. So this can be verified from the simulation. It goes to 4, 3, 4, whenever one agent is leaving, joining again, and so on. So in this sense, I can say that if you compute some algorithm based on the blended dynamics, that is initialization free because that doesn't depend on the initial condition. That does depend on the vector field average. Okay, so in this sense, we can guarantee some robustness against the joining and leaving agents. Another robustness can be think in this way. We have an average consensus, as I said. If there is some small measurement noise or disturbance noise in the process, then it ends up with this kind of equation. And we see that this is very fragile because the matrix L has a 0 eigenvalue, which is not stable one. So even if you have a very small perturbation, you end up with non-consensus behavior. But here, even if you have a small perturbation for individual vector field, the blended dynamics still have this perturbation. But thanks to the stability of the blended dynamics, it doesn't go far from the target. So it just converges to a small value of n whenever the perturbation is small. So in this sense, we can say the node perturbation can be robustified in this kind of example. Actually, this idea is already published by the Slotin team before, 2010. And the name of the paper is How Synchronization Protects from Noise. And then they deal with the identical agent. But now I'm claiming that the emergent behavior by the blended dynamics is also robust with respect to the perturbation of the individual nodes, because the idea is the same. Here, this is coming from the nature. So whenever they say the robustness of the multi-agent system, they emphasize that local failure doesn't collapse down the global behavior, meaning that if we have a group and some agents are really bad or malfunctioning, but if you have many, many good agents, then the group is still okay. Okay, so here's a mathematical proof of how it goes. Because we know that individual agents will follow the blended dynamics. So if you have a few bad agents, but there is a more good agent, then overall behavior still remains in good. So here's an example or simulation. I simulated 4 Van der Pol oscillators. One of them is really bad. You see the pink agent doesn't have a stability cycle. It just goes to 0. So we say that is a malfunctioning agent. And everybody has a 4 different frequency, different magnitude, and one agent is malfunction. That is the case where there's no coupling. But if we introduce a strong coupling, then you see the pink agent is still working very well. That's because they are surrounded by other good agents. So they are communicating, and their vector field is somehow averaged, so that we have this kind of behavior. So we have a mathematical proof of that behavior. But let me see. Yeah, okay, so I can briefly explain that. So as you know, the Van der Pol oscillator is written down by the second order system like this. Here, let's say UI is a communication term. But from the nature, our lesson is that nature just uses single channel communication, meaning that the medium is already shared with the other agent. So they don't use 2-channel communication. They only use single channel communication. So the question is, by communicating scalar variable, can you achieve the synchronized behavior of the second order system or not? That was the question. But it ended with, if we take their sum, like xi and xi dot is a sum, and if we define the zi, then this van der Waals oscillator is written in the second order system, and then we can apply the blended dynamic theorem only for the second system, and then we end up with this equation. So this equation is the blended dynamics because we average the vector field of the second term, which is zi dot. Okay, so zi dot is averaged in this way. And then what we note is that as time goes on, all the zi hat will converge to each other so that this blended dynamics becomes so-called projected blended dynamics. This is second order system. And then we finally see that this projected blended dynamics has this single term, which is the average of the parameter. So if this parameter, some of the parameter is bad, but majority is dominating, and then it ends up with a good parameter as long as the good agent is dominant over the malfunctioning agent. So that's a simple proof. Yes, admiration. The last robustness is coming from this kind of a scenario. So let's suppose that we have many cells in our body or in our organs. So whenever the cells is created, there should be some production imperfection, right? It's not very complete good procedure to make the cell. So we can say that every cell is a van der Waals oscillator. Their parameter is mu i's, maybe a random variable. So for simplicity, let's assume that it's a Gaussian. So it has a mean of m mu, and sigma square is a variance. Okay. But from the previous slide, what is really important is not the individual value of mu, but their average. Okay. But then we know that this average of the random variable has a less variance divided by n. So meaning that if you have many agents, then even if you have a production imperfection, each effect is diminished by the large number of agents. Okay, so that can be proved by this kind of experiment or the simulation. So if you have a 10 agent, whenever you create this multi-agent system, their behavior is very different. But if you have a 1,000 agent, whenever I create with the same probability, then it ends up with a very uniform behavior in this way. So we may think maybe this is a nature's strategy. Okay, so rather than making a big, precise cell, they make a lot of cells. Maybe each cell is weak and very prone to error, but because of the large number, it ends up with quite robust organs or something like that. Okay. So that was the analysis part. But now I want to introduce some kind of synthesis part, meaning that if we think reversely about the blended dynamics, we can develop the idea of designing multi-agent system or distributed algorithm, which is the following. Step one is you just design your desired contractive or stable dynamics. This is what you want. And then you check it can be decomposed as a sum of the small vector field. And then if it succeeds, then you just distribute each individual fi to individual agents and make a strong consensus. Okay, this is the way how you can design the heterogeneous multi-agent systems. So let me show you some examples. The first example is the distributed observer. So this is simple linear system. We have A and C, and you have many sensors from 1 to n. Okay, so I assume that A and C are detectable, but A and CI is not necessarily detectable. So meaning that single sensor cannot build their own observer. They need to communicate with each other. They should even take some information with others. So the still remaining question is how you can design the right-hand side of individual sensors so that they converge to the true estimate of the states vector of the plant. Okay. And then we follow the previous step. The first step is we write down what I want. So which is just a well-known Rambam observer, right? So AX well, this time S. So S dot is AS times injection gain L times Y minus CS. Okay. But this L and C can be rewritten individually in this way. And then we realized this is nothing but the average of this pink part. And here N is the number of agents. Okay. And then we just divide individual one to give an individual agent. So this is the distributed observer. And this is a strong coupling part. And it works well. Okay, so in this way, we can design the distributed observer. Another example is a quite well-known distributed optimization. So there are many literature about this problem. So problem is the following. You have sum of individual function. And I assume the sum of individual function is strongly convex. And then solution can be easily computed if you introduce gradient descent algorithm like this. But then we realized that the gradient descent algorithm is nothing but the blended dynamics of individual gradients. Okay, so we just divide individual one to individual agent and make a strong coupling. It works well. So it just finds the optimization. So here we note one thing. We only need convexity, strong convexity of the sum. We don't need convexity of the individual agents. So this is a unique difference from the other literatures, because most of our distributed optimization algorithms require individual small fi should be convex. But what I'm saying is that convexity is an emergent behavior. Convexity arises as a as a result of the communication. Okay. Here we have another example. What I'm saying is that let's say this orange box doesn't have any mobility, so it can move. You want to go to this location, but you cannot move by itself. So there are many small mobile robots, and mobile robot can push or pull this orange box. Okay. The question is, I don't assign you go here, you go here. I don't assign in that way. They just randomly move around. And whenever they meet this orange box, they need to develop their own controller to decide whether they need to pull or push or how much force they have to exert. So that can be computed by themselves without any centralized commander or organizer. So in order to do that, what we need to do is we need to find the individual coupling, individual state feedback in Ki, such that the overall system is asymptotically stable at the origin, which is the goal. Okay, so what I'm saying is that I'm modeling this orange box as a linear system, so second order linear system. And here UI is where the individual robot is pushing or pull. Okay, so this is the linear system. And my strategy is the individual agent use this kind of linear control law, but Ki should be developed by themselves. So that's the problem or the question in this figure. So this is a mathematical interpretation. What I need to do is I need to design Ki individually so that they collectively stabilize A plus BK. But the question is, this Ki must be designed by agent I with the knowledge of A and B1, but they should not use the information of Bj and Kj, which is the others. Okay, so they need to develop their own. But the problem is, once K1 is decided, this decision will affect the decision of K2 and K3 and so on. They affect each other. So how we can solve this coupled information? Well, we propose the following controller, which is, first, you take a sufficiently large beta such that this matrix is Coolidge. And then individual agents just employ these two, this algorithm. So this algorithm is the following. This Xi is a matrix. Actually, it's a matrix of the Lyapunov equation. And you see this is coupling. And then this Xi inverse is making the individual Ki. So maybe we are curious why this works. Well, once you compute the blended dynamics of this matrix equation, it ends up with algebraic Lyapunov equation. So as time goes on, this S will converge to S bar. And this S bar is actually giving you some stabilizing controller like the LQR, right? And then because individual agent will follow the behavior of the blended dynamics, individual xi will go to S of t, okay? So in this way, the collaboration emerges. What I want to emphasize here is that initially this problem is not consensus problem, right? Because I want to design K1 and K2, K3, they are not the same. But intrinsically, we need a consensus of what? We need a consensus of the control Lyapunov function in some sense, because what we need is a consensus on the Lyapunov matrix P. In this case, it's S. Okay, so once you have a common Lyapunov matrix, then you can design individual feedback gain, which harmonically stabilize the goal. So I think that has some message here. Okay, so same message is here. In the smart grid, sometimes people want to solve the economic power dispatch problem. So this problem can be simply written in this way. We want to find x1 to xn, which may be all different, which actually minimize the sum of individual cost function under the constraint that its sum is the same as some design value. Okay, so again, what I'm saying is that this is not a consensus problem, seemingly, but what I need to do is I need to harmonically assign individual agent xi value such that it minimize the overall goal. So I want to skip the details, but typically how we can solve this problem is we introduce a dual function and dual variable, right? So it's a Lagrange multiplier here. And once you compute the Lagrange multiplier, you can compute the individual optimal values. So what I'm going to do is I want to try the consensus of the Lagrange multiplier, and the philosophy is the same. Seemingly, it's not a consensus problem, but intrinsically, what we need is a consensus of the Lagrange multiplier, which is a hidden variable. Once they agree on Lagrange multiplier, then all individual values cooperatively do the task or do the goal. Okay, so in this sense, consensus may be still important. Why I'm saying this one is that when I started this kind of a study, people are saying that, okay, consensus is a mathematically interesting problem, but they don't think it is important because it's easy, just everybody gets the same. But now I want to emphasize that, okay, that's just one layer. But in a different layer, if we see the problem differently, even if it doesn't look like a consensus problem, but there should be some hidden variable which needs consensus. Okay? Of course, there are no systematic way to figure out which hidden variable is suitable for individual problem, but I believe always that kind of hidden variable must exist. Okay, so far I showed you several different examples, but always I use the linear coupling case. So K times summation of something, which is written in this way. But actually the main idea is if you enforce a consensus, then the emergent behavior arises. That's the main message. The way how you enforce consensus could be different. Yes, please.
The Lagrange multipliers.
Yes.
Can they go to infinity or go to minus infinity?
No. We just think about the bounded Lagrange multiplier in this case.
How are they bounded? Because you solve that.
Right.
Okay.
Yeah. So let me explain it.
Okay.
This particular problem, our assumption is that the problem must be feasible. So all the solution must be within the bound.
Okay.
Then Lagrange multiplier doesn't diverge. But if this setting violates the feasibility, then Lagrange multiplier diverges.
Yeah.
So people can.
So it's, observability is the key.
Right. Feasibility is the key. Yes. Right. Yeah. Thank you for the question. Right. But people can detect whether this problem is feasible or not because they monitor the Lagrange multiplier. Yeah. They go forever, then they realize, oh, this problem may be infeasible. Yeah. So, yeah. Right.
Very good.
Yeah. Okay, so let's go back to this slide. So I said this linear coupling that I always used. But actually, what is really, really important is that this UI term satisfies this so-called balanced action property. So meaning that all time their sum must be 0. Under this condition, you can introduce whatever coupling term you like. For example, linear coupling or PI coupling, or you can use sine function like a sliding mode control, or you can use nonlinear coupling in this way. So all of them actually enforcing consensus, and they end up with the blended dynamics. It's an emergent behavior arises. So I don't want to go into detail, but there could be many things. And then sometimes we realize, wait a minute, maybe nature doesn't use that kind of linear coupling. Nature doesn't use that kind of sine function coupling and so on. What nature is doing is something like an impulsive coupling in that way. They just sometimes burst or something like that. So how we can, yes. So how we can mimic that? So here now we go to the expertise of Ricardo. So we introduce some kind of hybrid system. So what I'm saying is that individual dynamics always flow through the continuous dynamics, but sometimes they communicate with a jump of the state, and they have some averaging effect. Okay, so I don't want to go into details at this moment, but we recently published a paper here, and the idea is if the jump is frequent, then we are enforcing consensus. Well, that's reasonable, right? Because we frequently make the average so that we are enforcing consensus. As an outcome, a new behavior arises, which is a blended dynamics. Okay, so I can skip that. Okay, so here, some of my students sometimes said, one day said, okay, what about this? In the airplane, we know that there are 3 flight controllers because we know one of them may be malfunctioning. So what they do is that they always voting. Okay, so what about this? If we have a neural network and we know neural network is weak, sometimes they lie or something like that. So we just identify 3 neural nets. Sometimes their answer is 337. But how we can make the majority voting without any centralized unit, with some kind of a distributed agent there, like a neural network, and then how we can figure out, we can eliminate the outlier. Well, we end up with the median operation. So median is just you are taking the middle value. So in order to do that, we typically think, oh, I have to collect all the data, and I just sort, and I just pick the middle. Well, there are another way. If you compute the L1 minimizer, which is actually this kind of thing, this is you are adding individual one, you minimize, and that's nothing but the median. Okay, then idea is simple. If you compute the gradient of this L1 norm, you end up with the sine function, and you treat this one as a blended dynamics. You split this one individual one. So individual agent just simply use the sine function as their vector field and communicate. So that's all. So in this way, you can compute the median over the given data. So what I do is I just do this median thing in this layer so that they always give the number 333, and finally we get 3. Okay, so this one way. By the way, I was talking about biological system. So if this communication is not biological style, then it's not very realistic. But fortunately, recently, the Professor Shim's group, they just published some communication method, so-called neurospike communication. So it's like a 1-bit communication. So it's like event-triggered control. So if you have data, then the 1 bit is very frequently transmitted. So again, I don't want to go into detail, but if we introduce that kind of neurospike communication in this layer, we get this kind of outlier rejector in this network. Okay, so that is also possible. All right. we're also interested in more complicated behavior. So you see this kind of a picture. So the swimmer approaches the school of fish, and the fish suddenly move one direction. So it's quite interesting to see that kind of a thing. So we just do some simulation. Here, what we do is, okay, there are many agents, and initially their breathing pattern is all different, but I already introduced some coupling. So they are synchronized, but yellow is the sunlight. So if the sunlight is shadowing more than half, then their pattern suddenly changes. Immediate change happens when sunlight covers more than half. So how they have this kind of abrupt change? Well, I think this is a little bit complicated behavior, but the idea is simple. We just use different layers. What I mean is in the very bottom layer, we use the median cycle that I just showed you. What I mean is the sunlight is 1, shade is 0. And then if you compute the median, then you can immediately get to know more than half is on the sunlight or not. So that's the first layer. And this information is transferred to the second layer. Second layer is a Van der Waals layer that I showed already. And then now what I'm doing is I'm just manipulating this coupling strength so that the blended dynamics is not just the average. Now it's weighted average. So by playing with those weights, we can control the breathing pattern somehow. So I believe if we do this kind of more and more layers, then maybe we can generate much more complicated behavior of this multi-agent system. That part is not very well explored, but that's our future work. Okay, so now I think I have 10 minutes somehow. So within 10 minutes, let me just briefly talk about the third property. So I already showed you emergent behavior arises as an outcome of enforced consensus under heterogeneity. Robustness arises from many different ideas. And then I haven't talked about the adaptation in multi-agent system. But actually, yes, that's true. In the literature, there are not many studies talking about this adaptation. So because this is quite new, we just narrow down the problem in this simple. So what we are considering is the following. We consider heterogeneous multi-agent system. Okay, but this heterogeneity is coming from the same function times different parameter. Okay, so this is a parametric uncertainty or something like that. It's like an adaptive control setting, right? So you can easily recognize, oh, this is similar to adaptive control. Okay, so theta I is a column vector. Psi is so-called regressor. Okay, and then what we want to do is I want to have a model, mathematical model that explains these parameters get close to each other as time goes on. Okay, so how we can develop that kind of algorithm which do some adaptation. Well, I just rewrote this agent. One simple answer is the following. We just introduce average consensus, then all theta converge to each other, and we are done. But we don't like this question because of the following. So let me just tell you about this kind of kindergarten setting. So in the kindergarten, I imagine that initially all the kids are in chaos, right? So everything is in chaos. But there is a teacher, and teacher is enforcing consensus or synchronization. So as time goes on, the kids' behavior is somehow synchronized. And later on, even if teacher disappears, their behavior is somehow synchronized. What happens? I think their internal behavior is somehow adapted to each other. And during this adaptation, no kids are communicating their internal variable, right? So it's just synchronized with others, but their internal variable has been adapted. So based on that idea, our proposed equation for adaptation is the following. So here you see G is just a small constant parameter, is a gain. And psi is a regressor. So now we use psi transport, which is column vector. And now I recycle this coupling term here. This is a product of these quantities. Okay, and then the question is how we end up with this idea. I think that's the key point in the next slide. So in this slide, let me show you how we end up with that equation. So first one is that, as I said, if blended dynamics is contracted with a large number of K, you get this one. So we know this behavior, okay? Oh, by the way, this happens after some positive time T hat, which is not important, but we get this, this relationship. And then, well, it's not very straightforward, but by working on some math, we also end up with their derivative also has this relationship, okay? And then this xi dot is nothing but this individual agent. And this blended dynamics is nothing but this one where this theta bar is the average of individual parameter. Then we need to do some interpretation about this term. So what is this? If you move this green term to the right-hand side, and if you employ the xi is similar to s, then you end up with this kind of thing. So the meaning of this sum is actually difference information between individual agent with the common. So if the value of this term is large, that means, oh, I'm very different from the common. If this value is small, that means, oh, maybe I'm very close to the common. So that kind of information is already captured or embedded this coupling term. So we can utilize this term to extract the information how individual agent is different from the common. So this is what I proposed before. But if you replace this one with this one, you end up with this equation. And now I think people are familiar with this last equation because this is very same as the adaptive control, right? So here, this is column vector, this is row vector. So if we introduce persistent extension of this matrix, then we end up with individual theta I will converge to theta bar. Well, we should be careful because in the classical adaptive control, theta bar is a constant. But here, theta bar is the average of everyone, including myself. Meaning that if I'm changing, then this theta bar is also changing. Well, of course, it's 1 over n, so maybe the ratio is different. So we have to play with those differences in the proof. And then finally, we end up with everybody converge to each other. So that's the idea of this adaptation law. So simulation results without any coupling, they are all different. But with the strong coupling, they look similar, but not the same. But now we introduce adaptation, then it takes time because the small g is very small. So it takes a long time until individual parameters converge to each other. But I believe this kind of thing is very similar to the nature, right? So in order to adapt myself in a new time zone after the long flight, it takes a long time until I adjust to the new environment. So it takes time. It is not a quick process, okay? So that's one thing. Mathematical proof is the following. In order to do that adaptation, we need two assumptions. So first assumption is that initial parameter, maybe they are all different. Initial parameter must end up with stable blended dynamics. Well, I think this is acceptable. Again, let's go to the jet lag example. So if I just came from Korea to here yesterday. So yeah, I need some time to adjust my time zone. But what I'm saying is that I'm not diverging. I'm not dying. I'm still oscillating with different circadian rhythm. So this is the same. In order to do the adaptation, the blended dynamics should not be unstable. It should be stable, but with some different parameter. And then with the slow adaptation, they will converge each other, but they need to still maintain the stability of the blended dynamics. So that's the first assumption. Second assumption is, of course, the persistent extension. So in order to adapt myself to the new time zone, I need some oscillation. Otherwise, no, I cannot adapt myself. So that's the second assumption. And finally, the theorem says with a very small value of g, which is 1 over square root of k, and k is very large, okay? then individual value will converge to the common, and also individual state converge to S of t. So that's all. And I can skip the proof. Well, proof is different. So even if I showed you this kind of intuitive proof, but this is not very rigorous proof because we have to deal with the underlying set. It's a complex set, something like that. So we have to introduce the Lyapunov function, and math is messy. Okay, so yeah, but I can skip that. Final example is like this. You have 3 pendulum, and they are all different lengths. So their natural frequency are all different. But if we turn on the adaptation, now the pendulum is adjusting their lengths, So eventually they become the same length. So as an outcome of the adaptation. Okay, so let me wrap up my talk. So I talk about 3 items. Okay, so first item was how emergent behavior arises for a group of agents. And I emphasized that emergent behavior is the outcome of heterogeneity plus enforced consensus. Okay, so diversity is necessary because individual agents need level block, so different block, and then we need to enforce. Second one is about the robustness. So I talked about robustness against the noise, disturbance, and faulty agent, production imperfection, joining leading agent. All of them is based on the stability of the blended dynamics plus averaging effect, large number of agents, and finally enforced consensus was important. The last question was adaptation. And adaptation is also enforced consensus over heterogeneity was necessary. And then we exploit the coupling term, the information, how much I'm different from the common, okay? And finally, we need a slowness. All those things end up with adaptation of multi-agent system. Okay, that's all. And all these works is done with my former students and also my colleagues. And I thank again Ricardo for accepting my visit. Thank you very much.
Thanks to you for the great talk. And we have time for questions.
Yes, sir. Thank you for the great talk. I have 2 questions.
Yeah.
The first one is on the distributed automation slide.
Distributed observer?
Automation, sorry.
Okay.
So you generalize the condition from the individual convexity for each term to be the whole convexity, right? The convexity for the whole objective function. Does this affect the claim for the convergence rate?
Right. Yeah, convergence rate is of course decided by this gradient. Okay. So there should be 2 convergence. First convergence must be very quick, which is all different agents should be converged. Do some approximate consensus. That can be controlled by increasing this gain K. Okay. So if you increase this gain K, then every agent quickly converges to some value, but this value is not the optimal one. So that can be accelerated. And then it follows the gradient of this capital F, because that's a blended dynamics effect. Okay, so it ends up with how much fast this capital gradient of capital F is. Okay, so the convergence rate is just depending on this gradient descent method, not individual agent consensus. Okay, so that maybe that answer your question.
Sure. The second question is that instead of like having a common coefficient K for the consensus regulator,
Yeah.
if you're going to have an individual one, that's a Kij inside the sum,
Right.
do we have some new findings, new or insights?
Yeah, I think that's a really good question. So, yeah, I know people are complaining, oh, everybody needs to know the same value of K. Yes, that's true. I think in nature, maybe the K are different. And then what happens if Ks are different? Well, it happens that you don't get the average of the blended dynamics. You will get this weighted average of the individual agent. We can prove it. So K will consist of the graph Laplacian, and graph Laplacian will have a left eigenvalue, eigenvector, and that eigenvector, individual component of that left eigenvector is actually this theta I, which will gives you the blending effect. So if you have a totally different Ki, then you get totally different weighted average. Maybe that is useless. But what I believe is that in nature, his eyes are not exactly the same, but they will similar to each other. So if you have a large number of agents, then maybe their overall effects may be similar to the averaging of everyone. So maybe that answers your question. Thank you. Yes.
What I really like about this talk is I think this is another way of looking at model order reduction. That we can, what every good engineer does is you start out with the simplest possible dynamic representation, and then you find out through testing that it's not good enough.
Okay.
Now, this is sort of the opposite way down.
Yeah.
You don't bother working with each individual molecule of a dynamic flow. Instead, you start with something that you can make a reasonably good approximation there too, and then come down to some kind of a set that you want to, and then you work up again after you put it in the laboratory.
Okay.
Yeah, so this is kind of the way I do engineering anyway, theoretically, let's put it that way. Okay, so
Thank you.
what I'm concerned about, though, is that if you generally apply this to a standard black box engineering feedback control problem, that you're going to get a very conservative design.
Yeah.
And that you really have to take into account the response feedback. You generally, the art of good feedback design is getting at least an acceptable response time.
Okay. So you're talking about the acceptable response time is necessary when we have a really black box to analyze. Yeah, maybe you're right. That's something I don't know much about from this perspective. This is, just starting from the
This is wonderful because you can indeed somehow justify model order reduction.
Okay.
So I love it for that. Yeah.
Thank you very much.
Okay.
But that kind of a thing, black box and the response time is something I didn't take into account.
No, of course.
Yes.
No, this is very good. Just as a side order here, that I actually go the other way around. My own research is I look at the word corpse, C-O-R-P-S-E. That's a dead issue. What I am interested in is something called NORPS, where you take out the C and you put in an N. Okay. And that means nearly optimal parameter system estimation. And that's what I can do. Now, I find also that Sean Main's stochastic approximation algorithm, I combine that with Leonard Jung's recursive prediction error method, and I can do it optimally.
I see.
And I'm just submitting that. I could finally prove that last April.
Okay, I see. Yeah. Thank you for the comment.
Now I got to implement it in analog hardware. Got to find a student to do that.
Yeah. Any other questions?
I have a question about the parameter estimation. Okay, so you might, for a system, I'm considering the case where you might not want your states to converge, but you do want the parameters to converge.
I'm sorry, you're talking about this parameter
near the
convergence?
Yeah.
Okay, so please go ahead.
I wonder if that's something you've looked into where, can you get consensus where the different x's don't necessarily converge? But well, what I'm thinking is maybe if you have the outputs, like you map them through some function, so you might have hi. So
you are talking about there is hi of xi, which is the output function.
Yeah.
Okay, then
so you get those all converging. So they have like outputs that converge. So for the case of the Van der Pol, it might be
Yeah.
when they're on the limit cycle, they all have the same output, but they don't have to be in the same phase necessarily.
Well, okay, so
Is that making hand?
well, that I think that could be a good question, but honestly speaking, this is new research, and this outcome will be presented in the coming CDC next year. But the thing is, I'm only consider this scalar dynamics. So this is just a single dynamics, and I haven't thought about that kind of a multiple vector and output function. We didn't get yet that. So we just started, and also proof is already complicated,
Right, yeah.
but I don't know. I never imagined alpha function, something like that. Sorry about that. But maybe in the future. Okay. Thank you.
Okay, I have a question about the contraction assumption.
Okay.
And well, that would be my main concern applying the result, because almost, even though there is this blended feature that is somewhat saying that you have exponential convergence on that auxiliary state.
Yeah.
And for nonlinear systems that could work, but the Miller Slotin paper treats very specific cases.
Right.
So this contraction condition, do you know if it is necessary?
No, it's sufficient. So there is some room to relax or extend this kind of thing, right? But yeah, we didn't get much about that direction. We just applied this kind of thing, many different contexts. But what I want to show you is that depending on different coupling, sometimes we assume asymptotic stability of the convex set. So that was relaxed. I mean, instead of contractility, now I assume there exists an equilibrium point or it's not equilibrium, compact attractor, which is asymptotically stable. Then we get the similar result using this linear coupling. If I introduce PI coupling, I need exponentially stable compact set. Why all these are different? Because initially I introduce a time-varying Fi. And time-varying Fi means I can consider some external input or disturbance as well. And then blended dynamics may not have equilibrium point. In that scenario, contractility is easier because you don't need any equilibrium points. So that's the reason why we introduce contractility. But if you have equilibrium point, sometimes asymptotic stability is enough. I mean, asymptotic stability over the blended dynamics, compact attractor over the blended dynamics. Sometimes I need the exponential stability and so on. So in the whole study, what we are realizing is depending on individual stability notion and the graph or method, always some blending effect arises. But of course, it's depending on the context, which stability you choose, which graph you choose, and something like that. So maybe there are more rooms. Maybe we can relax contractility rather than exponential stability or something, but that way we didn't go that far. So yeah, there could be something.
Because I guess with that assumption, then you can break down the analysis into two pieces, right? You pretty much deal with the nonlinearity through contractility that gets small, and then you use the coupling terms to do what the consensus does. But to me, it seems like even though that works, it doesn't really exploit the nonlinearity, and it's almost treating the nonlinearity as some converging dynamics, which might be necessary. So there might have to be some convergence, but maybe not contractility, maybe more like incremental stability of some sort.
Right. I do agree with you. Incremental stability may be enough, but our mathematical skill didn't get yet that. So so because philosophically, what is important is enforce the consensus plus some kind of stability. That could be anything, but you're right. So maybe there could be incremental stability is enough.
Okay. And then you didn't make the connection, but maybe it's behind the details. But you have this 1 over k or 1 over n order bound, right?
Yeah.
So is that a typical bound that is after some time, the trajectories will have this norm bound?
Right. After
Is that invariant?
Is that invariant with respect to what?
Right. Like, is it almost like a semi-global
Right,
practical,
right.
or because you talk about the stability properties, but I wonder whether there's a next step to prove semi-global practical,
Okay.
because
So,
it's just convergence, right?
right. We didn't talk about the underlying set today because it complicated the part.
Okay.
So it's actually, yes, you're right. It's a semi-global practical things. So you give me some complex set for initial condition, and I compute the K star, which is a bound. And with over that bound, I can guarantee that error is big O of 1 over K. Of course, there should be some coefficient in front of 1 over K. And then with that 1 over K, I can guarantee the practical stability. So it's exactly the semi-global practical stability thing, which I didn't show very well.
And the set you converge is a diagonal.
It's diagonal?
Like the consensus set, all the states are the same, or is some other?
Right.
set?
So the consensus set is diagonal.
Okay.
But on that diagonal set, there is a motion.
Correct.
That motion is decided by the blended dynamics. And then what I'm saying is the stability on that diagonal set.
Okay.
So you know what I mean. So on that diagonal set, whether we have a compact attractor or whether we have a contractility, all those questions happen on that diagonal.
Okay. So you're looking at what is called pointwise asymptotic stability on the set.
Yeah. So when we analyze everything in the singular perturbation thing, initially it is pointwise convergence. But of course, pointwise convergence is not a very practical one. So of course, it also happens after some time, like a Tikhonov theorem. After some time, we can approximate the solution with SOT. So that is also possible. Exactly like a Kari's textbook. We also analyze the singular perturbation in the pointwise sense first, and then we can decrease the solution time. So that's what we did.
All right. I think we have exhausted our speaker. Did you come yesterday?
Yeah, I come yesterday.
Early.
I already disclosed that. Okay.
Any questions in this room, or we are good?
I have a question.
Please, love.
Okay. So if the agent synchronization is not due to the coupling, is not a coupling base, but imposed by something external, for example, timing or safety constraint, would that your approach, could work, or could say something, or how that could work?
I'm sorry, I cannot understand completely. Ricardo, can you catch?
Yeah, Adolfo, can you repeat? I understood.
I'm sorry.
If the coupling is not due to if the conversion is not due to the coupling, then I got lost too.
But so instead of that, is maybe something external, like a timing or some safety constraint, for example, for safety critical systems, for the aerospace.
Okay, so I haven't talked anything about safety constraint or state constraint, state bound. I didn't talk about anything regarding that part. I believe that is kind of how we design the blended dynamics. So if you can design the blended dynamics in that way, okay, so let's say, so if your blended dynamics has a good behavior, then individual agent will quickly follow that. I'm just repeating what I said. In that way, you can ensure some state constraint, but not from the initial time. So I need at least convergence time. But after that, everything is just following the blended dynamics. That's all I can say regarding your question. But honestly, I haven't thought about that kind of things like a safety constraint or something like that. Did I answer your question?
Yeah. Thank you. Thank you for your call. It was a very nice presentation.
Okay, so thank you again.
Okay, thank you very much. Yeah, I see.
That's fine. Yes. All right.
Where's your copy? You finish it?
Yes. One second. Let me have one. Yeah.
Very good. I'm pleased to meet you.
Yeah, it's nice.
Yes.
So let me do one thing. Yes, are you going to the presentations? I won't be able to, if you're going there, I can spotlight. Yeah, maybe we can talk to them. Or I go to the. Let me go there and meet them. Okay, perfect. Or, yeah. I'll send you I'll send you a WhatsApp message. Sorry? Can I send you a WhatsApp message? Yeah. I have a in this. Okay. No, thank you for coming.
Good to see you guys. I come up to campus every now and then, but I'm going to be leaving, you know.
The angel only when?
April Fool.
Okay, so we have time because we want to schedule a seminar in the winter.
Yes.
Okay.
Yes. I've already talked about that. There.
Yes, we just have a schedule for
Yeah.
room for the schedule. But
Good. Yeah. He's meshing it all together. He said. I just talked with him.
I'll reach out to you for good dates.
Okay.
Okay. Thank you.
You bet.
Bye bye.
Yes.
Okay, so thank you. Yeah.
Okay.
So we have something for you. By the way, it's sometimes that's your question. Like a link to that. That's my forget that. Very nice guy. Yeah, please. Thank you. Thank you. Bye bye. Bye bye.